There is a lot of information in the glacial and periglacial landscape chapter, and so I've broken it up into 3 smaller lectures. It's all so important to Alaska and to the stuff that we see on a regular basis. I wanted to make sure not to give it short shrift. The first thing to talk about is what is glacial ice, and this goes without saying, of course, that glacial ice is a product of snow. But it's snow that's gone through a metamorphosis and change over time. The metamorphosis of snow that actually produces avalanches also impacts the way that snow forms into ice over time. Freezing and thawing of small particles of snow eventually compact into a type of ice that is called firn. That firn is sort of like the beginning of glacial ice that is then compacted. The compacted glacial ice, which is the blue glacial ice that we're familiar with seeing in Alaska, is quite distinct from the hard, brittle ice that you would find in your freezer. When it collects in mountainous areas, this ice forms alpine glaciers, and there are 3 major types of alpine glaciers. Cirque glaciers and also hanging glaciers, which are related to those, are confined to the mountains either in the small cirque bowl or hanging along the side of a mountain ridge. A valley glacier is much larger in size and is usually a product of many smaller cirque glaciers feeding into it. The ice is literally flowing down through a valley and carving and sculpting as it goes. If that valley glacier spills out onto a flatland area, it is known as a Piedmont glacier. And any glacier that finds its end or terminus in water can be called a tidewater glacier. Of course, in Alaska, the most famous of the tidewater glaciers are the many glaciers that end in the great fjords in southern and south central Alaska. In addition to there being alpine glaciers, a number of parts of the world have continental ice sheets, which are found where they are not because they're high in elevation, which leads to the accumulation of snow and ice, but because the snow and ice is accumulated because temperatures are relatively cold in those areas. This then forms larger ice caps and ice fields that don't spill out the way that the alpine glaciers do. These are most common in Antarctica and in Greenland, but we can also find them in a few other places, including northern Canada and Greenland. Here are some pictures that show the different types of glaciers. This is a Cirque glacier that hangs above Raven Glacier in the Crow Pass area. And you can see that the glacier is mostly confined to this small bowl-like area. On the right-hand side is more of a hanging glacier that might be sculpting and carving a bowl, but isn't quite there yet and is hanging onto the side of this mountain. Mendenhall Glacier down below is a classic example of a valley glacier that spills out of the mountains of southeast Alaska and onto a relatively flat area. When it completely spills out into a large flat area, as many of the large glaciers do along the lost coast of Alaska, then we get a Piedmont glacier. Good example of a tidewater glacier here, a valley glacier that reaches the water, I believe, in northwestern fjords. And this is glacier, the Kennecott Glacier near McCarthy. Here are a couple of ice caps. This is one that's in Iceland, and I think I misspoke before. I meant to say Iceland was one of those places, along with northern Canada, that has these large, more continental ice sheets in them. But the really large ones are found in Antarctica and Greenland, and cover large areas, sometimes with mountains protruding through them, which are called nunataks. Glacial ice accumulates over time because more snow falls than it either melts or evaporates. The term that sort of puts together melting and evaporation is called ablation. So where accumulation exceeds ablation, we can over time build glacial ice. Now on a glacier, some parts of the glacier are more likely to accumulate and others are more likely to be losing glacial ice. And so we refer to the area that is gaining ice on a year-to-year basis as the accumulation zone. More snow is falling than is being lost. And then the area that is down at the lower part of the glacier, as the diagram shows, is the ablation zone, where we have more melting and more evaporation than snowfall. In the middle is a theoretical equilibrium line. Now, most of you know, if you've spent any time on glaciers or looking at glaciers, that glacial snow coverage is pretty complex, and it's not usually a nice even line that shows us where that equilibrium line is. Although sometimes we can identify what's called by mountaineers a fern line, which is the line where we can see last year's snow ending and having the melting taking place any place below that. If we have more accumulation than ablation in a given year, glaciers grow, of course, and as they grow, they advance. If we are losing more snow and ice than we are gaining, then glaciers retreat. So that's what controls the movement of glaciers back and forth, up and down valleys. Now, in addition to that sort of movement, glaciers also move by the very nature of the ice, which is plastic-like, and so the ice sort of flows down slope over the course of a given year. That plastic nature of glacial ice is what is partially responsible for the formation of the crevasses that we see on glaciers. The top part of the ice is more brittle. It's more likely to crack and have fissures at the top. Down low in what's called the basal part of the glacier, it's much more plastic-like in nature. So as it moves slowly up and down over little barriers or around turns, the top part of the ice breaks, forming crevasses. The down part remains relatively plastic. Here's a picture that shows some crevasses in them, a little picture from within a crevasse, a couple feet down into it, and then looking down below at relatively old crevasses that formed much higher in a glacier but have pushed down lower and have sort of sealed back up in places. Down in that basal zone where you have the glacier moving in a plastic-like manner, you have a lot of freezing and thawing of the ice right down near the surface of the ground. That freezing and thawing is responsible for a lot of physical weathering that takes place at the surface of the ice. The water is penetrating little cracks, refreezing, breaking, and slowly what's called plucking rock from the surface of the bedrock that it's going over. As it does that, chunks of rock often get dragged along, sometimes polishing rock surfaces or leading to striations and scratches in the surface of a rock. This picture down here on the bottom right-hand side shows a small knob of rock sticking out at the end of the Mendenhall Glacier when this picture was taken. The Mendenhalls receded past this, much above this now. It is what's called a roche montanée, which is described in the book, has a very smooth surface on the sort of upslope part of the feature. On the back side of this, or the side that is, I guess you could almost say it's like on the leeward side, you tend to have a lot of plucking taking place. And so you get these smooth surfaces with a very rough surface on the downslope side. So these are just some of the different ways that glaciers do their work, how they're built, how they produce crevasses, and also how they engage in the erosion that is ultimately going to lead to the landforms that we see. And then when the glaciers melt, they deposit that material, and that leads to other forms of landforms, which we'll explore in the next lecture.